Okay, our next unit in probability is called independence, and this particular lesson is going to concentrate on understanding when two events are independent or dependent. Okay, you have in the previous lessons, in the very first lesson, we talked about the definition of, we had a formula like this, and it said the probability of A and B was equal to the probability of A times the probability of B given A. Okay, so you should be familiar with that. Now, if I were to solve that for this particular one right here, then I would divide both sides by P of A. So if you look at this, and I go, let's go divide both of them by P of A, and then it goes away over here. And that leaves me with, go away, stop. Anyway, my bad. Leaves me with the probability of B given A is the probability of A and B over the probability of A. Okay, that same kind of thing is, wrong thing, my bad, come back here, is this. Okay, so this is a definition of conditional probability, but I really want you to understand that it's just a variation of a formula that you already know. Okay, when you are looking for and, we multiplied two probabilities together. If we are looking for the condition, then we're going to divide two probabilities. And here it is written for you again. Up at the top there, I was just showing you where it came from. But one of the things that I want to point out to you again, something to just help you remember what it is, whichever one is right here is what's on the bottom. The top is always A and B. But if it's a probability of A given B, then we're dividing by the probability of B. Okay. So these particular examples are going to deal with drawing cards from a deck. So we need to review what you do or do not know about draw a deck of cards. Let's go with that. So first off, you need to know that a standard deck of cards has 52 of them, 52 cards in a deck. You have 4 different suits. And if you are not familiar with those suits, you need to know that there are clubs, skipping diamonds, hearts, and spades. And I'm running out of room. Okay. I don't know why my pen is not working. Okay, clubs, diamonds, hearts, and spade. Clubs are black, diamonds are red, hearts are red, and spades are black. So basically, when you have a deck of cards, you have 2 different colors, red or black. You have 4 different suits, and you have 52 divided by 4 means that you're going to have 13 cards in each suit. And if you know this is not a problem, but this is what you need to be familiar with when you're doing these problems. 13 cards per suit, and those cards range from ace through 10, and then you have jack, queen, and king. Okay, so keep that in mind as we do these problems. So consider drawing a deck, consider drawing a card from a standard playing deck. Let R represent drawing a red card, and Q represent drawing a queen. So the probability of drawing a red card, okay, you can go through the formulas if you want, or you can say, how many red cards are there? Well, if there's only 2 different colors, then we do know that half of those, but there are 26 cards out of a total of 52, or there's only 2 colors, one is red, the other is black, so the probability of getting a red card is 1 out of 2. The probability of getting a queen, come here, come on. The probability of getting a queen and a red, how many red queens are there in the deck? Okay, well, there's a queen of diamonds and there's a queen of hearts. So that means that there are 2 red queens out of a total of 52 cards in the deck, which means that's 1 out of 26. Okay, now, like I said, you can go through and use the formulas, but I think most people think that this is an easier method. Okay, so if you do want to use formulas, you might find someone to help you with that. Okay, find the probability of a queen. This one they actually have the formulas for here, so we'll go ahead and fill in the formula. Find the probability of a queen given it is red. So this is the probability of queen given that it's red, is the probability of a queen and red, which we figured out right here, which was 1 over 26, and the probability of red, which was 1 over 2, and if you keep change flip, that gives you 2 out of 26, which becomes 1 out of 13. But you could also say, given you have a red card, how many red cards do I have? 26 of them. How many of them are queens? 2. So that's 2 out of 26. So you've got to figure out what you're easiest with, what you can understand, and what makes sense to you to be able to move forward. Okay? Now, this next thing is very, very important. It is kind of the definition of independence. Two events are independent if the probability of A given B equals the probability of A, or the probability of B given A is the probability of B. The whole point of these, when you figure things out and you're working through them, if this little given part doesn't matter, then that means the two events are independent. Okay? If they're not independent, then they have to be, anybody know? Yeah, then my pen would let me write. Okay, if they're not independent, then they are dependent. So if they fail that test, you'll see as we work, then that means that they're going to be dependent. Okay, so consider rolling the event of rolling a 3 on a 6-sided die and the event of getting heads when flipping a coin. So they give you this possibility. We're going to roll a 6-sided die and we're going to flip a coin, and these are all the possibilities. So this is our what we referred to earlier as a sample space. What is the probability of getting a 3? Well, this one has a 3 and this one has a 3. So the probability of getting a 3 is 2 out of how many possibilities are there? 12. So that means it's 1 out of 6. Okay, the next one says, what's the probability of getting heads? Well, all of these have heads. So how many is that? That's 1, 2, 3, 4, 5, 6. That is 6 out of 12, which reduces to 1/2. Now, what's the probability of a 3 and heads? Okay, so if you look at all that we have, this is the only one that has 3 and heads. So that is 1 out of 12. Okay, you can go back to also remembering that the probability of 3 and heads is probability of 3 times probability of heads, and I'm going to stop talking. So let's keep going. Now, this next part says, consider now the conditional probability of rolling a 3 given the coin is heads. The sample space is now limited to only the outcomes that includes heads because, as they stated here, given the coin is heads. So when you're looking at your sample space, okay, what is the probability that it's heads? Well, we figured this out right up here. That's 1/2. What is the probability that it's 3 and heads? That is 1/12. Keep change flip. That's going to be 2 over 12, which is going to be 1 out of 6, which you can also see from here. I can't have these because they don't have heads in them. So the only one that has 3 in heads, given that it's heads, that means there's only 6 possibilities. One of them has a 3. And now, most importantly, the fact that the coin lands heads up does not affect the probability that the roll is a 3. We calculated 2 different things. We calculated the probability of 3 given that we have heads. And the probability that 3 given that we have heads is 1/6. And the probability that we get a 3 is up here, and that is 1/6. And since these two things are the same, then we know that these two events are independent. Okay, if they were not the same, then we would know that they are dependent. Excuse me. That's a very important concept that you're going to go through. And if you have to figure out whether two events are independent or dependent, you're going to want to figure those things out. Okay, so you're going to read through the rest of these packets. The one that you have on the next page has to deal with soda, buying a soft drink, and a pretzel, and whether or not they are dependent or independent events. Okay, when you turn the page again, we have a wonderful problem about the Titanic and whether or not you were a man, a woman, a child, had any effect on whether or not you survived or perished in the Titanic. Now, when you're doing these problems, one of the things that might help you talk among your group and help you know whether or not you're reading these problems correctly is to keep up with the notation, especially when you get into the ones that have a keyword that's important. If a name is selected at random from the list of people on board of the Titanic, what is the probability that the person survived? You're looking for the probability somebody survived. What is the probability the person is a woman? Probability it's a woman. I'm going to let you figure those out. What is the probability that the person was a child? But once we get down here, what is the probability that the person was a child and survived? That's the probability a child and survived. Okay, and that's different from this one down here because we've talked about how important that key word is. Okay, so this one is, given that the person perished, what's the probability that it was a man? Probability that it was a man, given that they perished. So those kind of things, when you start working these problems, I mean, some of y'all might not do it, but it just helps keep your thoughts organized and helps you realize, especially when you're doing it from these frequency tables, where you're going wrong and things are going wrong. All right, I hope that helped and y'all have fun figuring out which events are dependent and independent and whether or not that had any effect on people that survived the Titanic. Thank you very much.